Yeah, I want to welcome everyone to today's TRX webinar titled Enhance Your Generative Design Exploration. It's being presented by Altair Engineering Incorporated, as Jason mentioned, and Altair was recently ranked as the #1 software vendor for generative design by ABI Research. Altair is a global technology company. It was founded in 1985 and headquartered in Troy, Michigan. They're a global leader in computational science and artificial intelligence that provides software and cloud solutions and an artificial intelligence that provides software and cloud solutions, simulation, high performance computing, data analytics. They're also the creator of both the HyperWorks and Inspire software suites. Inspire is an intuitive and powerful family of software products, which you'll be hearing about today, and enables simulation-driven design throughout the entire product development lifecycle from the concept to reality. And when used early in the design process, the technology empowers the creation of designs that are focused on both performance and manufacturability, and that empowers its users to explore, develop, and then manufacture high performance products in a single intuitive development environment. Altair's software, as you'll be hearing about today, is used in almost every sector, including aerospace, automotive, consumer electronics, and sporting goods. In 2002, Altair aided in the design of the Airbus 380 wing ribs by applying topology optimization to reduce the weight of those ribs. The company also offers customer access to software applications from over 55 different software companies through its partner lines. So many industries today are currently exploring the design of freedom allowed by additive and hybrid manufacturing technology. So as a result, generative design and design exploration have become more widely used to reduce weight, cost, and time to market while still maintaining or improving performance and sustainability. So in this webinar, Altair's Tony Gray is going to discuss the workflow of designing a manufacturable part with Altair's Inspire software, including geometry, parameterization for design exploration, topology optimization based on the chosen manufacturing method, geometry realization, as well as manufacturing simulation. Tony has a bachelor and master's degree in mechanical engineering from Auckland University in New Zealand. He joined Altair UK in 1997 as a structural optimization specialist, and he first discovered topology optimization while working as a powertrain engineer at Ford in the UK in the early 90s. Since then, he's been very passionate about the practical application of CAE-based simulation and optimization tools for product design development, and his emphasis is on innovative design, weight and cost reduction, and improved cost performance. One key factor of this TRX webinar is that the attendees will be provided an opportunity to receive a free trial license of this Inspire software, along with some interactive training provided by Altair. So more information on that's going to be near the end of the webinar, but I'm going to turn it now over to Tony Gray of Altair and let him dive into the software and the presentation. Welcome, Tony.
Thanks, Scott. Thanks very much. Good afternoon, good evening, good morning, wherever you are in the world. It's 7 a.m. for me. So today's presentation is, as Scott said, designing a manufacturable part with Inspire. Hopefully not a software demo, kind of more of a brain dump, an opus of the last 4 or 5 years of designing for additive, predominantly processes. And I'm going to try and tell a consistent story kind of based around this rocker pivot mechanism in a motorbike suspension system. So here we go. I don't need to spend much time on this slide. Scott pretty much summed up my history, but yeah, I've been doing topology optimization related work for coming up to 30 years soon, but really passionate about the practical application of optimization for design engineers, and obviously focused on weight and cost reduction and product performance. So I'll keep on moving. So I think the kind of the elephant in the room is what is generative design, which is kind of in the title, and what it's a term a lot of people bandy around. So I think there's really 2 definitions. So the top one, that's my definition. It's just exploring, or design exploration, by generating and investigating multiple design concepts. Generating designs and trying to find the best one. And I guess at a higher corporate level, it's about all the tools and technologies that allow you to do that. So it's the tool set HPC for huge numbers of runs that you might generate, software that anyone can use to democratize it. But it's that, yeah, the whole thing that wraps around, designing, using the technology to create lots of design ideas and to find the right one. So we'll be working through that process today, and really I'd like to kind of show with this next slide that it's nothing new. So this happened pretty much at the time I joined Altair in 97, get my decades right. My colleagues in Germany were doing this work with VW, and nothing much has changed. You started with your design space and your loads, you ran your topology optimization, you got a result. You had to interpret that result and try and get some usable geometry out of it, which could take some time. You had to then throw your geometry over the wall into the CAD department to get them to build you some geometry you could work with. You then might take it back and do shape optimization, some kind of detailed sizing, and come up with a final design. So that process, it looks pretty simple on the small screen, but it could take probably 6 weeks to run through that process if you're lucky. And design iterations were difficult. And the problems there are kind of the same problems now. This kind of information is pulled out of a engineering.com study, look at simulation prototyping practices. And the key issues are, getting geometry out, handling complex geometry, capturing the physics, doing design for manufacturable parts, capturing the results, geometry, and then manufacturing simulation, because you don't want to do all this stuff if you can't manufacture it. So today I'm really going to be focusing on this, how to create manufacturable designs with a bit of the stuff around it. And one of the most interesting things is that, on average, engineers go through 19 iterations of the design virtual simulation cycle before the first prototype. So if you're going to do 19, you want it to be right, or really you want to, reduce those cycles so that you get it to the designable part quicker. So let's fast forward to today. This is just a kind of a snapshot of the process with Inspire. Start off with physics capture, then geometry editing, preparing your model for doing optimization, generative design, doing the optimization, setting it up for manufacturing, capturing that geometry, maybe exploring some design alternatives, doing manufacturing simulation, making any design adjustments, validating your final design, and then going into production. And I've kind of grayed around this area down here. And to me, that's what generative design is. And one of my colleagues kind of termed the phrase that it's a sandbox. Yeah, you're just playing around, trying all these different design alternatives. So I've stolen that comment. I really like it. So this is where I is my happy place, is just playing around and all these design alternatives, coming up with something interesting, and that's where we'll be today. So quick coffee break. To start with, I'll give an overview into Inspire, the family of products. I don't want it to be a sales pitch or a demo, but really Inspire is this kind of group of different softwares. They all have a common look and feel. They're all intuitive to use. Most importantly, they play really well together. We'll mainly look at Inspire, so that's structural design and optimization and motion analysis. A little bit of Inspire casts. I'm not a casting specialist, so I've utilised colleagues to help me there. All the renderings that you'll see have been done in Inspire Studio, and then we'll be looking quite a bit at Inspire Print 3D as well, which is kind of embedded within Inspire structures. So what really is Inspire? Is kind of it's got this really strong geometry foundation, designed to do simulation-driven design and computer-aided industrial design. The physics, setup of loads and load cases is really designer friendly. The kind of generative design, topology optimization, there's also topography and size and shape, but it's all really easy to use. So I know democratization's been used a lot in the last few years, and it really does make it easy for anyone to use it. Manufacturing simulation, so there's all the different manufacturing tools, and it's extensible. It's an open platform, so if Inspire's not enough for you, the file formats allow you to expand into the greater HyperWorks to use OptiStruct itself or HyperMesh to do more advanced simulation. So it's powerful in itself, but it also opens up the world. And just an indication, I built this slide a little while ago of just all the functionality in Inspire. When it was released 10 years or so ago, there were only 8 icons in the GUI, and now there's all this functionality, which is quite overwhelming when it's all put on one screen at the same time. But a lot of what we've been done has been developing tools and processes that support the way a designer works on real parts. So that's a lot of my focus. And the idea is to get an integrated design environment that lets you quickly go from your concept design to a real part you can print. So again, I'll just try and simplify that. The tools will focus on building and editing geometry, capturing the physics, and we'll introduce the motion stuff, design optimization, design exploration, and then print simulation. We've got SLM and binder jet sintering. So I think before we really get into the generative design and what it is, there's some fundamentals. So no matter what kind of optimization or generative design process you're going through, you'll need these fundamentals. So let's look at them. So again, we're going to look at the suspension pivot, the blue part in here. We'll look at traditional casting of it. So that's a no inserts casting. So, and then an indirect. So that would be printing your sand mold or printing a polymer sacrificial part. We'll look at design for SLM, design for binder sinter, and also design for extrusion plus machining. And we're looking at the single part, but there's nothing to stop you doing multiple parts in the same simulation run. So try and keep it a little bit simple for the presentation. So the first point is you need to either create geometry or import it from a CAD system. So in this case, we're looking at importing the geometry. So we support and Inspire a whole bunch of different file formats, as you can see there, all the main ones. And geometry is never perfect, especially for complex assemblies. You might find that you have overlapping parts that in the FEA world, it's not a happy place to me. Just broken geometry, surfaces missing. So we even have customers that use geometry as their primary CAD cleanup tool, just because it's so easy to use. So you import your geometry. There's some things you can do like partitioning, just makes up or makes later processes easier, where you ensure you keep your connection points are just always there in the model, helps downstream workflow. So yeah, often it's these processes that you need to learn. So not just the tools, but there's some really slick workflows that can really help your design. So this is the raw imported geometry you see there. Bit of partitioning was done, and then I haven't used the motion product within Inspire for probably more than 6 months. And when you have mechanisms, it's really important to make sure you capture the loads in a part correctly. If you just put a single static load on, you might get it wrong. If you don't have your boundary conditions correct, you'll probably get it wrong. So without getting the physics right of a problem, you've got no chance of getting a good design. So you don't always need this motion analysis, but when you do need it, it's very easy to use. So in this case, it took me around 15 minutes to set this model up, coming from, not using it very much recently. And you can see, just after analyzing the motion, you can interrogate the loads pretty simply. And it's also really good for just visualizing you've got your model set up correctly. When you've got that motion set up, it's pretty much a single click to then do an analysis. You can see the behavior during the run. You need, and at this point, you've got to ask yourself the questions for your design. What are you interested in? Are you interested in mass, stress, stiffness, displacement of parts, normal modes? So you've got to have your model set up so that it can capture the things that you're interested in. So, often it's stress or safety factor, and weight to be minimized. So stress limit, minimum weight, very typical setup, or maximum stiffness for a given amount of material is also a very typical setup. So, we've just gone a single click on this button here after running the motion analysis, and we get the full FE results of the part. So the next stage is really you want to prepare your model for optimization. So we're showing here in the video just Inspire being used to build a design space. So the brown design space here, that's where you want to do your domain. You want to do your generative design or your topology optimization within. So the more space available, then the more optimum your part will be. One problem with doing this build in Inspire is often that the CAD world owns the packaging space. So my background in automotive powertrain, it's always paid to get the CAD guys to build the design space because they know how much clearance it needs to surrounding parts, etc. And if you do that, it's actually really easy to re-import it back into Inspire. And another key point is if you've got your maximum design space and you go and do your optimization and you can't meet your targets, then there's pretty much no way you're ever going to meet them with that design space. So the earlier you know that, you can go back, request more package space, get someone else to move their part, whatever. So very optimization very early is very important to help the design process. So this is just really quickly showing the replacement of the existing part with external CAD data, generating CAD. And the nice thing about doing it this way is that in that replacement process, it keeps all the connections and contacts with other parts. So just going in and I don't know if that will replay, replacing the part, setting up with a right click, define it as a design space, just there, then picking some symmetry constraints, so this part will be symmetrical, so just defining a symmetry plane. And then, you've got that done, you want to, it's not that complicated all the time. So in this case, we want to do a topology optimization, we want to maximize the stiffness, and this is kind of a generative approach here. We can pick, I want to maximize the stiffness at these multiple different percentages of material. I can control thickness, so that's how member size control between certain sizes. And the smaller that is, the smaller your mesh has to be, the longer the run will take. And in the analysis here, or the optimization, this is set to use all 30 time samples from the motion run. You could reduce that to, in this case, maybe just 3, sort of the start, middle, and the end would probably capture it for you. And then you hit run, and it will launch depending on how you've set your files up. So my computer's set up to let 4 parallel runs. It'll just shoot off up to 4 parallel runs and solve them. So let's see what it comes up with. So, and these ones took around 5 minutes, 5 to 10 minutes to run from memory. And we've got these 3 different results. You can, when you post-processing them, you can compare results. Just again, a one-click button, you can compare the mass. So I should have had the mass of just the part here, but it's harder to see the difference. You can see the compliance. So less compliance means a stiffer part. So again, the bottom one with 30% material you'd expect to be stiffer. But you can start going through, picking out key structural elements that are going to be common amongst all of them, compare results, and even look at the orientation. So if you're thinking of a certain manufacturing method, you can spin your model around and kind of evaluate it for potential manufacturing approaches. So it's getting knowledge. And again, once you've got that, we're looking at the results here. There's a single click analysis button. So that's a no meshing involved, really fast, solves in seconds to minutes. And you get a really good idea of performance. You can ignore the results like really high stresses around sort of sharp contact regions, but down in smoother parts of the model, you can totally believe the results and really early on decide whether your design is going to be feasible. You can also, again, there's a single click fit polynerbs button down here. So that the direct results of optimization can often be a little hard to visualize. When you've turned them into geometry, like the polynerb here, they can be easier. So again, a single button click at different thresholds of density can give you a real good idea of your geometry. So these are like the core processes. If you do know other optimization, if you do this either in your design process for your structural analysis, it can be really helpful. And about 20 years ago, I was actually showing optimization and OptiStruct to a potential customer and didn't have a background in this stuff. And he gave me the 3 best quotes I've ever heard in the one meeting. And he said, he said, OptiStruct, I've changed it to Inspire. It's a thinking tool. So, and then he goes, it gives you hindsight at the start of the design process. And it's not the answer, but it gives you a really robust starting point. And that's true. You get to a concept really early on to develop. So you're starting from something that's reasonable based on the physics that you've given it. We've done some generative design. We've looked at a few different options, and you could just at this stage figure out which of those material percentages might meet your requirements. But this is the basis of all. All that follows is that you need that fundamental sort of baseline analysis and optimization to get started. So let's move on. I've got a lot of slides to get through, so I'll go fast. So let's do a generative design for permanent mold casting. So I used an image of a wheel. My master's was in fatigue and fracture mechanics of alloy wheels. So let's get right into it. So optimization for a permanent mold casting. So there are many manufacturing constraints we can apply and Inspire. There's different symmetries. So again, we want to apply the or you've seen us apply the symmetry in the previous one. We've also got the single draw, split draw, radial extrusion, overhang constraints. So split draw, you can see we've applied that to the design space. And what I wanted to do here is kind of demonstrate how it's really easy to set up, again, what can be called a generative design approach. So in the Y draw direction, there's no real other orientations you could sensibly select. But in the Z direction, you can apply it at Z equals 0 degrees, and then really quickly, it takes seconds to rotate your draw direction, launch a run, rotate it, launch a run, rotate it, launch a run, rotate it, launch a run. So, this to set up and run all these took less, or to set them up and launch them took less than probably 2 or 3 minutes. And then at the end of it, you get all the results, you compare the results. And in this case, we can look at the 30 degrees and the 120 degrees gave the best stiffness results and very, very similar masses as well. So that would say to me, okay, these results are worth investigating further. I didn't, but what you could do is maybe start at 120 degrees and do, 3-4 more runs at 2 or 3 degrees either side of that 120. Same at 30, and that way you'd get another range of results, and you could very quickly zero in on what is the best from all of these. I'd already done the analysis previously on a different orientation. So what I did was essentially I've aligned. I did another analysis. I refined the mesh size, so you can see the discreteness of this results improved. I did that by reducing the thickness constraints, almost a half. Some element size is halved, and this is the free optimization. When you look at that, it kind of a clear draw direction starts to show itself, and you can see the result in the swing arm. We have very, very clean looking design. So there's no hard and fast rules how you come up with the angles, how you interpret your design. But for this case, with the draw direction aligned to that face, or normal to that face, we came up with a clean, very clean result. So again, early on, does this work? So with the casting constraint, we've got this option called porosity. So it's just all within Inspire. Single click, choose your material, choose an element size, hit run. Runs within seconds to a few minutes normally. You can very quickly check these basic results, which if you understand casting, you'll know more about than me. But solid fraction, temperature over time, so you expect that to drop to 0. Solidification time and shrinkage porosity, I think, is in solid fraction of the two that people look at most often. So if you've got small amounts of porosity, a casting engineer will say, I can design risers and my casting process to eliminate those. If you've got huge areas that might not be designable out, you'll need to go back and potentially update your design. Go back, update your model, do it early before you've invested in lots of detailed CAD. And again, the one-click reanalysis for the structural as well, that just works on your optimization results. No geometry needed. Get an idea of that performance. If you don't think you can design out any, say, high stress raises in kind of general geometry areas, then you need to review, update your model, or change your material or design process perhaps. So we're almost through the casting design. So we've got the feasible concept that you're kind of happy with. Now, I didn't do this. Again, one of my colleagues worked on this part for the CAD a couple of years ago, and it takes hours or days to generate CAD. CAD is expensive, but came up with a very nice functional design, has draft on it, is manufacturable, and then again for casting you need to defeature, like remove the holes. So this is here to here is trivial in Inspire, but you're designing for the casting process in this stage, not for function or for structural function. You've hopefully already done that, and then you want to confirm that performance, so get the mass, and so get the von Mises stress, find out where the maximum is. It's very much at a high point around the hole, but you can quickly determine the general stresses in the part. So just actually one note, when you traditionally when you build CAD like this, just anecdotally, the weight tends to go up because you start adding material. By adding material, you often decrease the stress from the previous kind of single click reanalysis, and you increase the stiffness again, the increased material to get that designable part. So yeah, often design improves, but weight goes up a little bit. So when you're confident in that, then you want to go ahead to the casting simulation. So again, we've got a product called Inspire Cast. Looks and feels the same as Inspire. Very quickly set up your casting design. You build your gates, your runner system, your risers, and again, it was built with just a very simple runner system, and then it was redone with some risers to try and eliminate that porosity. So not my area of expertise, but just kind of showing some of the result types here. So this is showing the temperature over time. So the mold filling and the temperature, and the one on the right is solid fraction. So as it cools, so shows that it's a pretty good design, should be manufacturable. Go ahead and manufacture it. So this is the kind of the complete process. Baseline part, package base developed, free optimization for some general feel for the design, the generative study, detailed casting constraints, quick feasibility for both casting and performance, concept development, so detailed CAD generation, perform that, confirmation, do some casting simulation, and then manufacture it. So it's pretty easy, all within the Inspire tools, except for the CAD generations was actually done before we had proper sketching within Inspire, so that's the proviso there. So the next one we'll look at is generative design for sand 3D printing. So I mean, this to me is just one of the coolest things. It's casting being one of the oldest manufacturing technologies, and 3D printing being one of the newest. So it's just to me, it's a very, very cool technology. So this is the result of our the design for a draw direction constraint. So there's a few options, but what I like to do is we've got some semi-automatic polynerve fitting technology. So I won't play the whole video here, but I can quickly go through and choose that my polynerve is going to have symmetry, create the polynerve around the selected optimization results. So you can see it overlaid there. Do some Boolean operations to make sure it all lies within that design volume. Just quickly fast forwarding. So you can see there how it matches up with the bosses that have stayed in the process. So, then you could possibly, Boolean those together, do detailed geometry, like filleting around the connections and stuff. But this whole process here, took 1 minute and 24 seconds. So, and you could print the mold and cast this part as it is. You need a bit of detailing because you've got some stress raisers, but just before you even invest in that, don't forget we've got the quick checking. We can check the performance, just rerun that model. You can see that now we're at slightly lower mass rather than that traditional design was a little bit higher because we're adhering more closely to the optimized geometry, not needing to worry about the draft angles and things like that, and also the performance checking of the casting can be done. So we didn't do the casting on this example, but need a slight detour because we never printed this part. But earlier on, we went through this process for this design, which we'll see a little bit later on. So there was detailed design, defeatured for casting, so we filled the holes in. Also added material on any face that might be machined because you need to allow for the tolerancing there. and set up and simulated the casting. So we've got the temperature at the top and temperature at the. So this is the filling stage at the top and the solidification stage at the bottom. So the simulation of this was done, and our friends at EX1, they printed the sand mold. It also included inserts, so it was built to in the same way that we simulated it, with the 4 parts within the mold. Printed the sand part and cast the result. Sadly, I don't have an image of the final cleaned up, polished part, but from memory, it looks really, really good. So that that is the whole process. A real part came out the end of it, and fantastic job by EX1 doing that. So now a design for investment casting. So another detour away, because I haven't done the pivot for this process, but it's very equivalent. So this bracket was for an instrument panel and a helicopter to support the instrument panel. Again, this investment casting is a pretty cool process. You print the part with the polycast material, so it's instead of a wax pattern. Most of the design in it is designed for the casting requirements due to thin members, and after the first run through, did the design, the casting expert said, worried about these 2 legs distorting, can you update your design? So that's very, very easy to do in Inspire. Just added a brace in the polynerd model and updated the design and checked the performance. So this was a project with Mueller, and they used solid form to actually set up the gate design. We did the filling simulation and solidification, no issues, and shrinkage voids were all within the runner system. So that confident in that after the analysis that the design would be worth manufacturing. Fast forwarding, there we go. So again, want to manufacture it. There are a couple of issues. The cost of printing the full part was quite high. It was really going to be a squeeze into the printer as well. So the decision was made to split in half and then glue it back together. So again, all these little bosses and stuff in that splitting with the lug and sockets, that was all done in Inspire. The printed assembled pattern here, it was then cast, so that's the cast part. It doesn't look it in those photos, but it is. So it was again a very successful process using that design process. So next is design for SLM. So this is probably more where I've been spending my time at this and binder sinter in the last few years. And what you find is that every time it's a trade-off. You want lighter parts, you want low material usage, but you can't have it all. So you start generating supports if you want lighter parts, and there's no right answer. You orientate something vertically, it takes longer to print. You can get more parts per print, but you get more distortion. So it's never easy, and calculating the cost can be very complicated. We worked on a project recently, and the cost on some parts was just really really high when you wouldn't expect to be, and not too bad when you would expect it to be. So many factors contribute it, and it's very important to understand what your trade-offs are and what your costs are going to be. So very similar process to we saw before. There's an overhang constraint that you can apply to the design space. So we did just a free optimization using 50% of material, so no part orientation. Guided by the result of this free, we did an orientation up this way. We also flipped it over, did it the other way, oriented it to that short flat side, and then oriented it to the long flat side. So really quick setup, essentially a generative design study, quickly assess the two I like the look of with this, the free guided and the totally free. And you don't need to explicitly choose one particular result. You can take features from all your different, generative results and just kind of interpret them. It's not a hard and fast thing that you have to live with. You use Inspire as a thinking tool, and then if you start doing some manual polynerbs, you can include really kind of unusual print considerations during the build. You might need to allow for depowdering and binder cinder approach, but what you want to do is use probably a manual polynerb approach, and there's meant to be a video here. Oh, it's on the next slide, to let you do those rapid iterations and get from your print to your structural really quickly. So this is the video I thought was going to be on the previous slide. So this is the manual polynerb process. Again, it's for this similar part, and you can go through and work on your optimization results and start building geometry that reflects your results. So again, I don't really want to play the whole video. I want to play more than that though. So letting me fast forward it. Again, just wrapping around the results. So something's going on with my the screen here. I think it's better. Right. Again, we can go through, start making a really nice polynerb. And the good thing about this is they're very easy to manipulate. You can, again, like with that console bracket, we could added that cross brace. You can consider orientations. It's a really sort of complete design process. And we'll just go back. So one other thing that I like to use is if I've got, say, a 45-degree overhang constraint, I'll sketch guidelines into my model as I'm building. So you can see from looking at these different orientations, and I've built up these to try and make it on the build plate. Demonstrate this interpretation like this. So then when you're happy with your results, and I did have possibly do a demo in here, I won't do it because of time, but the process is we've got this print 3D and Inspire, and we can choose between SLM and binder jet. So this is the SLM process. So you select your part, you can define a printer. Again, this process takes minutes. We can then orientate the part based on a face, or we've got tools to set it up and optimize the angle. If you need to create supports, you can create different types of supports and realize them. You can slice your model and review the cross section. So another, when designing for SLM, balancing the sections is quite important as you build your model. And then the inherent strain approach we use for the SLM, you need to print this coupon in your machine. Once you've printed the coupon, we provide the coupon STL file. You can just export it out in this calibration phase. You measure this distance D1. You quickly run an analysis that creates a material which captures your printed parameters. So that's your calibrated material. then you choose that calibrated material for your print run. So a bit fast there, but so you can see that as the print runs, you can see the displacement of your part, get the von Mises stress. This is during the print process. Important result is this collision distance. So this, you have a recoder height, so you want to avoid recoder strikes. So this is very important metric as well. Layer shifting, so you can get kind of marks appear in your print, and then we also calculate a failure index. And then there's also a spring back phase. So you can see how much your part springs back and any residual stresses after the printing. So this spring back is very important to get your final net shape. You want to know that it's close. So again, you would probably change your design that you printed to add material that could then be machined out, kind of in the key connection points. So, and in the real world, we printed this with Renishaw. It's the real world. We went through about 8 design iterations. Partway through, we did some test prints. We saw these snap lines, thought to be due to an unbalanced section. So, and these quite large radii, causing this surface quality issue. So we redesigned it, shifting things around a bit, and in the end got a result that was getting through the print simulation fine. We again confirmed the performance and then printed a bunch of them on a Renishaw printer. So again, really successful process from start to finish. So binder sinter now. I've been doing a lot of design for binder sinter recently. Again, there's different requirements, but for those that aren't familiar, there's kind of 3 stages. There's the printing the green part, and you can print almost anything, but that green part is very fragile, so you have to be careful. Then you put it in the furnace, and as it heats up, it becomes a brown part, and it loses a lot of structural integrity until it finally solidifies into a fully dense part. So a lot of design for this is that sintering, making that brown part not collapse. So you need to keep the CFG low. You need to try and create self-supporting geometry, avoiding too much overhangs. Big sort of height to thickness aspect ratios are bad. So again, overhang constraint and single draw are both useful for designing for binder sinter. You can get some very nice results out. So I use both in this case. I like the overhang constraint better just for this particular model. I've used the single draw in the past. The auto polynurb here came out beautifully for quick assessment. Also did a manual polynurb approach, and again, you can consider your printer guidelines and get more detailed if your actual optimized design doesn't meet your requirements. So with binder sinter, sometimes you can print on a flat base, so it's a fully self-supporting part like this, or you create live setters, so you actually print a part that your part of interest sits on, and then it shrinks at the same time. So the shrinkage is in the order of 20% during the sintering process. So these are kind of the two strategic approaches. For this presentation, I've just shown the potential of the one not on a setter, but again, this is the print 3D process for binder sinter. So quickly go through, you define your part, you define your oven size, you orient your part in the oven. So again, that was just by selecting the base part. There's a very cool SAG preview tool. So again, this takes seconds to run. It uses our SimSolid solver in the background. So you can quickly assess, and this is looking at the material properties of the brown part to see if you'll have a SAG issue, and you probably would in this case. And then you want to do your sinter analysis, so you can go to the run. You can control your oven temperature profile, include gravity effects. You can scale your part initially if you want. You can do just a compensation run, which we'll do here. So this is iterative to try and compensate for the part shrinkage. And there's a bunch of advanced parameters you can control as well. So it's more interesting to look at results. So after running this, it did 3 compensation runs. So you can see the first one, it starts off at some nominal size and then it shrinks down. The second one, it starts a bit bigger and it still shrinks past. And the third one, it gets pretty close to the final part. And you can see the reason it's not lined up here is that it's actually shifted along in the on the print bed. So some more results. There's relative density, volume change, interlaminar crack, interlaminar crack, and layer orientation. So they can also be assessed. So again, another small detour to the real world. We didn't print that part, but we have a similar part we printed. First time we sintered it, it cracked. There are 2 things that the engineers didn't like. It was this cross brace here causing deformation and just this kind of weak point through the hole where it cracked. So we went through a few design iterations, filled in the hole, made a pocket in here to reduce some mass and remove the cross brace. And that's the sintered green part looking pretty good. Sintered part looking pretty good. And if we went back and looked at the prediction, we were seeing some cracks across there. And back to the desktop metal part. This was the real part, so it being taken off, polished up, and then sat back on the setter after the design process. So again, all pretty good. So I know I'm going pretty fast now. Design Explorer for generative design. So within Inspire, we have a tool called Design Explorer. Before getting started, it's based on being able to parameterize stuff in Inspire. So pretty much we've got all these sketching tools that we can parameterize pretty much anything we sketch. So, that cast, traditionally cast part, if you knew what you were doing, you could build up a parameterized model of that and use those parameters for optimization. This is just an example I've got of a honeycomb, which I've built. So equations for the way it fits together, the size of the honeycomb, the cornered radii of the box, the width of the box. So once you've got your model parameterized, you can go back and do studies of stiffness or whatever on these parameterized parts. So Design Explorer allows you to do a big design exploration based on this. So you can create an exploration, create your design variables. So that in this case, I'm just doing direct modeling, pushing and pulling surfaces and using those distances as design parameters or as design variables in my model. Again, this is for an extruded type part. So we've learned now that we can go from an extrusion constraint, we can get this nice clean part with polyNAD fit, check the performance. So again, I've created an extruded section and this is what the push pulls are happening on. So Design Explorer, create an exploration, we can do DOE or optimization, set up all our design variables with maximums and minimums. So again, I had 8 or 9 of them here. Define our responses and goals. I'm interested in stress and mass in this part. My objective is to minimize mass with a constraint on stress. And then I can run an exploration. So there's potential to do multi-execution depending on what you're doing. We can either run OptiStruct or SimSolid in the background. So SimSolid's our very fast meshless solving technology. So you can follow up if you're interested in that. And then here's the results. So you can, there's a lot of exploration possible. We can do, this is showing the mass as it converges over time. So mass reduces, stress staying within a constraint, different scatter plots of mass versus stress. And we can, find our best run. We can load the results from different runs. We can sort them. You see as I load the different runs, the geometry will change and the where the maximum stress will change. So there's a very thin member in that one there. So you can see there's a lot of data there, feasible and violated results. So really powerful tool to do a real big generative design on a model that can be parameterized. So that's a summary. Summary time. Just about on time. So we've gone through this process with generative design. We've done a traditional casting. We've done a sand casting, although not of this part. Giant binder jet approach, SLM approach, and the extrude machine approach. So that extrusion design explorer optimized could then be finally manufactured. So this again, just a recap of the process from baseline all through manufacturing constraints. We looked at print, cast, extrude. We didn't look at molding. We didn't look at forming, but again, any manufacturing process hopefully can be handled, all the typical ones within Inspire. And then just I guess the proof we haven't. We're not just talking the talk. We're pretty proud of our optimization history. Been leaders for around 25 years. Recent ABI research award. So we've been at the leading edge for quite a while. And as Scott mentioned at the beginning, we'll follow up with emails to you about details of how to get a trial license of Inspire and access the training. We're kind of going through a bit of a change in our license process at the moment. So timing is everything on that. So we will be in touch. So that's all 2 minutes over, but we started a bit late. So thank you very much. I did have some extras if we had time.
Yes, Tony, this is Scott. And I know we're over time, but there is a couple questions if you have a few minutes to just remain on for
Sure.
those questions. The first one came in is you discussed maximizing the parameters like stiffness and or weight. Does the software account for the final part cost in the design process?
We've had many discussions, and we'll hopefully be addressing that. It's one thing that I'm really passionate about is trying to capture all the results and all the different, all your different designs. You need, it's a lot of bookkeeping when you start generating a lot of stuff. And if we can do that bookkeeping properly, we can hopefully start capturing kind of cost out of that as well. But if you can build a cost model, then we do have a vision in the future to be able to capture that. And in OptiStruct, people have built cost models in the past based on like volume of material and process.
Great, thank you. Another question is, based on this comes in from Janae. Based on everything I've seen on Inspire so far that you've presented, it seems almost very overpowering or overpowered. And are there any weaknesses or features that it really doesn't have that you would focus on?
We kind of, I think I get the question. It can be overwhelming. There's so much power there, but I think once you've had some training, that's simple. The features we're adding and working on, there's more manufacturing constraints. So we're doing like a 5-axis milling constraint. One thing that I'll show is part of my extras. We've got some implicit geometry technology that we're integrating. So we purchased a company about a year ago called Gen3D with this Solus software. So this is very advanced implicit modeling. So we're going to integrate that. That'll allow sort of real good control of lattices and just bringing that into the part. So I'm not sure if that answered the question, but it's some more information.
Yeah, because the software does, seem to provide everything that you would need. So I guess the question is what else is there that you see possibly? But another question in regards to by someone else that may link into this is, does the recoder collision simulation take supports into account?
Yeah, if there are supports being printed, they will be included. Yeah, my model didn't have any supports in it. My my desire whenever I do these things is to try and design for no supports, because that's what customers want. Not always possible, but that's what I strive for. And other things I didn't touch on, we do actually do design lattice optimization as well. It's not something I'm a big fan of. Not a lot of practice and parts I've worked on, but it's yeah, we only just scratch the surface today.
Cool. So I'm going to piggyback with a question in regards to the overpowering representation of what the software can provide. At what level does someone have to be? I know that the intent of this webinar is to highlight, the software, as well as give everyone that participated the opportunity for the trial license in some manner. What level of a designer, I mean, can you be entry level and still get benefit from taking the training? Is there training modules that are geared towards, different levels of design, or do you got to be really in the weeds to understand it?
You can get going pretty quickly, quickly and easily. There's like included in the installation. There's actually, you don't even need to go to the training. There's a bunch of getting started kind of videos, and that's just your basic mouse clicks and yeah, how to move things around and basic geometry editing. And you can stay at that, basic geometry editing, basic optimization, and it is simple. I've trained people in probably half an hour to do those basics. It's when you start getting into the more advanced stuff that it gets complicated. I mean, even people that come from a designer background often will pick up like the sketching and the geometry stuff, better than me who comes from a CAE background. So I'd say, there's people that pick it up almost instantly, and everyone's different. Some people take more time, but I think it's possible for everyone.
Awesome, thank you. Well, there's no more questions there, and as Tony mentioned, there'll be a reach out to everyone that registered via email in regards to getting that trial license set up. If you're interested, that'll be a follow up. And then just to anyone new on this TRX webinar series, America Makes is continuing its mission to expand and accelerate the footprint of additive manufacturing and 3D printing. And so that's why this medium of these technical review exchanges were set up and created. So by creating this platform, it's allowing us to have the additive manufacturing community and 3D printing community come together and share knowledge and experience, within itself. So if you or anyone on here on the call, if this is your first time and you're very interested in presenting, Jason Thomas is on the call. You can reach out directly to him or through the website, through the America Makes TRX webinar series. So if anyone else on the call from a different organization is interested in highlighting, feel free to reach out to Jason. So, and I again want to thank Tony for taking the time to present Altair's software, and everyone on the call. Look forward to follow up communication in regards to the free licensing period. Jason, do you have anything
Thanks,
else?
Rob.
Yeah, just
Thank
a quick
you.
addition.
Yeah, Jason.
Just a quick addition. If you are interested in the free trial that Tony mentioned earlier, please enter it into the chat or the Q&A at the end. Just how can I get access? And we will pull a report and we'll be able to see that, and then they can contact you. So you can either reach out to Tony directly or just enter it in the chat and Q&A now, and we'll reach out. So Tony, any final remarks?
No, just thank you for everyone that attended, and for you guys for setting up.
Thanks, Tony. Great job.
Thanks, everyone. Have a great day.
Bye.